Hey everybody, welcome to Deploy 2024. So thrilled to have you all join our virtual conference. We have a great lineup of speakers and really cool sessions, ranging from our cool technical demos around AI and other latest technologies, fireside chat with our leadership team, customer success stories, and you'll hear from our technology partners and from our product leaders and our engineering team. Multiple sessions throughout. So sit back and just enjoy. I'm Abhi, and I head the developer relations team here at DigitalOcean. And when we decided to do this talk at Deploy, I was pondering over what would be a cool demo to demonstrate. And I stumbled upon this interesting statistic where um, apparently around 28 billion photos get uploaded to Google Photos on a weekly basis, and this was sometime in 2020. I can't even imagine what that number is right now. So one thing led to another, and I found myself deep into this rabbit hole of building my own cloud storage and photo editor app. We've all done that, right? You find something and you'll be like, "Oh, that is cool. I want to build that." And then you quickly realize how complex of a system it is and how really complex it gets so soon, right? So you need to take a step back and then try to do it in incremental fashion, and that's the talk about. It's going to be my learnings and what I how my journey to build and continue to improve this application is basically a photo editor app that'll be powered by a technology that we'll dive into is gRPC. It's Google Remote Procedural Call, and using our very own object storage solution called Spaces. At the end of the talk, I'll be happy if you learn a thing or two about gRPC and protocol buffers and their capabilities, um, and how one can leverage cloud storage solutions to build distributed systems. But the most important thing would be if you get inspired to go out there and build and break things and not be afraid to pick a new technology and try it out. Like when I started work on this. I did not know much about gRPC. So, yeah, here we are. I might know a little bit more now, but it's a journey and you got to keep trying and keep doing it so that's when you get comfortable being uncomfortable. So, go out there, pick a technology that you think it's too complex and try to be relentless about your approach and build something and break something and enjoy, have fun. This is the 30,000 foot view of what we're going to build today, or what's already been built, and I'm going to just show you. It's not going to be a live demo session, but we do have like um, it's not going to be a live coding session, but we do have like a demo at the end of the talk. So stay tuned. So that's me with my hoodie, and I'm trying to send a photo over to the server. We're going to make some edits there, and then it's going to get uploaded to the cloud. Simple, easy peasy, right? Let's double click on it and see what's going on under the hood. Um, there is a client and a server module here. The client is going to send or send the, the picture over gRPC um, to the server, and the server is going to do some processing, and then finally it's going to upload that to our object storage solution using a really cool tool called rclone. It's basically, I don't know if you all use the rsync. It's a Linux utility that synchronizes files across systems, and rclone is the rsync for cloud storage solutions basically. um, so in this case, the edited files that have been saved locally will get synchronized to the instance Spaces instance running in Amsterdam, and then they'll also be copied and synchronized across New York and Sydney. and then we'll be able to generate a quick share link, and you can send it to your friends, and folks across the globe will be able to download and enjoy your precious moments and what you've captured, right? There are multiple components here, but in order to understand all this, we need to first understand what this gRPC is, what are its benefits, and then we'll go into each of these components and see how they are all coming together. gRPC, remote procedural call. Remote procedural call is a protocol that allows a program to execute a procedure or a subroutine on another physical machine across the network, as if it was like a local procedural call, abstracting the complexities of network communications. Well, this enables distributed computing to be seamless because it's as though you're making a functional call, but it's actually being uh, performed across different systems, across different networks. Google in 2015 took this and then leveraged the benefits of protobuf or protocol buffers and HTTP2 to combine them to form something called gRPC. Um, what is a protocol buffer? I don't know if you've heard. Some people might have heard or might worked with protobuf. So it's a language neutral, platform agnostic mechanism for serializing structured data, and it excels in creating like strongly typed contracts or APIs in this case, where each field is clearly defined with specific data types, and this ensures data integrity and reduces error. And so basically, the protobuf serializes the data into a binary format and reduces the data transfer size and sends it across the network when compared to yeah, it improves efficiency when compared to like text-based formats like JSON. And being strongly typed, it's a well-defined and validated structure of data, so this reduces the likelihood of errors and other mismatches when data is exchanged between services. So it's quite preferred in distributed systems. Then you have HTTP2. It's a major revision of the HTTP 1.1. And one of the key features of HTTP2 is that it allows, uh, it has, and has multiplexing, which basically allows multiple requests and responses to be sent simultaneously over a single TCP connection, thereby reducing latency and improving speed. And it has something called binary framing, which is actually encapsulating the data into smaller chunks of data frames, um, and and it's sent over across the network. It supports full duplex communication, which literally translates to bidirectional data flow. So in this case, the client and the server form a channel or a connection, and then data can be transferred simultaneously between the two services at the same time. Um, so, with all these combined, it makes it an ideal candidate for high performance, real time, reliable communication between services. And so, in the next slide, I'll show you a example of how we can define a proto file or the API, so to speak, in a language agnostic way, and then we'll see how the code is generated, and um, we'll go a bit further. So on the left side, what you see here is a proto file for the service called storage in our case, that has a RPC, remote procedural call, a method or a function basically called upload, that accepts a parameter image, and then it returns a storage response. And the structure of the image is defined at the bottom, and the storage response as well. Basically, it's a string field where you're going to store the name, and then there's this bytes field where the data is actually uh, the the image data binary is populated basically. Um, One of the advantages of using gRPC is that it has the proto C compilers. So what it does is the protobuf compiler is able to take this language agnostic definition file and then generate a client and a server implementation on your preferred language. So they support multiple languages. In this case, I've chosen Rust, uh, but you could do it in Python, C++, Go, and they support various other languages. So you take the file, it compiles it into and generates a client and a server stub, and then you'll need to extend it and implement the custom client and server logic to handle whatever you want to do, right? And you don't have to understand the code here. That's not the purpose of the slide. It is to show you how flexible gRPC is and how easy it is to generate these things, these stubs, so that we can uh, yeah, make the implementation quicker, and it's much more error uh, proof. So what is happening under the hood? Okay, first things, this is Wireshark. Some of you may know or may not know, but it's a packet analyzer and a network analyzer tool. It's really, really powerful. Uh, since the data has been sent in the binary format, and we need to be able to snoop into the network to be able to capture the packets and debug and analyze. Maybe that's one of the tricky parts of using gRPC, is that debugging might get a bit tricky. Um, but in this case, it's quite straightforward here. Making a call, upload, and sending this data over. As you can see how the fields are clearly stated there. You have abi-1.jpg file with the data being sent. Um, and then in the next slide, you'll be able, here you could see how the server responds back with a response string that the image has been saved. So basically, an image was an unstructured data turned into a structured data, serialized, sent across the network, and of course deserialized and processed on the server side. And then the image has been stored, and then a response has been is sent back to the client. That's what's happening here, and we'll definitely show you the code and the demo in the upcoming slides. But this is to give you an overview of how this functions and what happens under the hood. Like I said, that we could go a bit further and more technical, but I want to stop here and not uh, because it's better if you see what's happening. And I'm also trying to show you how to debug stuff and how you could leverage tools like Wireshark to be more productive, and especially while handling gRPC, right? And then the images have been saved, um, and then we need to store or save them somewhere so that's globally accessible. And that's where scalable object storage comes into play. So Theo offers a robust object storage solution called Spaces with built-in CDN capabilities. It ensures fast and reliable content delivery. And it's fully compatible with Amazon S3 bucket. So if you have some workloads running there, feel free to. The migration is quite straightforward and quite simple. In fact, we can also use the AWS um, S3 command line tools to interact with. Spaces object storage as well, fully compatible, and the transition is going to be seamless. So and of course you're going to save a ton of money then, right? And we have spaces across 8 different data centers. So the high availability catering to various geographical demands is met, and it's really important in when you're building a distributed system, right? and trying to put everything together from the bird's eye view. So we went a bit deeper, 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 and now you're seeing um, the whatever we've covered so far, um, and that is you have a proto file with the definitions. And in this case, I'll be using Tonic, which is a Rust library or Rust um, crate, we call it, which you can which is used to compile this proto file into a Rust client stub and a Rust server stub that you see here. And then the client is actually making a local function call to the stub actually, and then we'll see the whole process of serializations, binary conversion, sending it across the stream, deserialize, and all this happening. And then you have rclone, which I already mentioned, that has a rclone spaces config file. I won't be revealing it because it has my spaces keys, access key, and secrets. But it's basically you have the configuration file, and it uses the configuration file to connect to different buckets, and you can define multiple um, use cases, and it's quite flexible there. Yeah, so this is what is happening under the hood, and this is what we are going to see as well. Let's deploy. The first thing what we're going to do is some code inspection. I'm going to move away from the presentation screen, move into the code editor, walk you through the project, and then we'll start running a demo or something. Yeah, cool. Right. I'm keeping the architecture diagram on the side so that you'll be able to connect with every component that we are dealing with, and then you'll be able to like relate, okay, this is where we are, and I'll walk you through it. um, as I said, this project is completely built using Rust. uh, don't ask me why. uh, and if you're not familiar with Rust, it doesn't matter. You could do this whole thing with any other programming language as well. um, but if you're familiar with Rust, yes, then or if you want to learn Rust or want to explore, like I said at beginning of the talk, if you want to try out something new, yes, please feel free to do so. I won't be going into like the details of how this, like what's the package manager and how everything works and how the build system works. That's not in scope. Um, the most important thing here, as I said, is to show you the demo and to see how the communication is happening and what is happening under the hood, right? Rather than the whole project setup, so to speak. Um, so you, yeah, cargo is like the package manager for Rust, and then here you define your dependencies. And as I mentioned, we're using Tonic, which is the crate or the library that I'm going to use for compiling and generating the client and the server stubs. Uh, And for the photo editing part, I'll be using something called Photon RS. Shout out to the folks there. It's a pretty cool library. It has a lot of um, yeah, image processing APIs that you can leverage. But in our case, it's going to be pretty straightforward. We're going to apply like multiple filters and to keep it just simple, right? And I'm using Tokyo, which is a async runtime. Cool. And here's the proto file. I've also added a download RPC, which might be a little different from what you see there in the previous slide, but it's pretty much the same. But you also added another method to download the file, and so this is the proto file. And then if you so what you see here, the Pixbox RS is the generated file, which has both the client and the server stub. Uh, So you see the generated client implementation, and you will probably also have the generated server implementation. Okay. Um, any changes or any method that you want to add here, you'll need to recompile, and then this Pixbox RS will be regenerated. So that's something to keep in mind, right? And then we do is you extend it by building a custom logic for your client, and this is the client code. Pretty straightforward here. Let me just walk you through the main. From the main, yeah, you're connecting to a server running on localhost at particular port, accepting few command line parameters here. In the case of upload, I'll be accepting a image path, um, and then if you look into the upload function, it accepts the image path, and I'm using the Photon RS library to read the image and basically turn this image, whatever image you've read, into the image format that we've defined, um, that struct that you saw in the proto file earlier, um, a string and the bytes for the data, right? Yeah, in this case, I've read the image and I'm now converting this image into the format that we've defined, um, with the name as a string and the data as bytes. You package it in that format, and then call on the upload method. This upload method is calls the client stub upload, the generated code, and like what we mentioned earlier, um, it makes a it feels like you're making a local function call, but it's actually, and it takes away the complexities of the network communications under the hood. So you're calling that method and passing the right parameters, and then on the server side of things, let's go to the upload method. So this method actually reads the data, checks for the valid fields, and then basically uses the Photon RS library to load the image, and convert the image from the bytes that it's received into a Photon RS image type, so that we can start playing with the library to apply some filters. So you have some I've hard coded some random filters that they have here, and randomly it picks one from the list and applies it to the image here. Um, and then it saves it in a local directory, right? This is a demo and still a work in progress, right? So um, that's why I'm like right now saving it to the local directory, but these are not like the practices that you do in production. And so this is just for the sake of the demo. Uh, be inspired by it, but don't start following this as a production readiness. This is far from being production ready. So, and then once you've saved the image, and if it's okay, you send back that image saved. And remember, in the Wireshark's slide, we saw that the server was sending back the image, saved image response, right? And this is where it generates. So this is the code structure and what is happening. Um, so right, and now it's the fun part. We need to see if this actually works, right? Okay, I have the server running here. Let me also open the make file so that you know. Okay, I wrote a simple make file with all the commands to run the program. So basically, a make run is actually going to run the server binary in this case. So the server is actually now running, and we have the client on the left side, and I still need to run the client command. And then I have a rclone script. So I have a script called rclone.sh, and that's running, that accepts a parameter, which is the path to the directory that you want to sync up to the cloud. So I'll be watching a directory locally, and then when the new file comes in, our clone is going to copy it and sync it with our Amsterdam instance of our spaces object storage, and then also synchronize it with both Sydney and New York instances, right? So this is running here in the background. This is one of the cool features of gRPC called reflection. Reflection is a feature that allows um, clients to dynamically discover services, methods, and messages types of, available on the gRPC server at runtime. So if I run this gRPC curl command, asking it to describe the Pixbox storage, it's gonna give me exactly what we wrote in the proto file earlier. So we have a storage and it says, okay, these are, and then if you want to describe them further, you can pretty much ask for more details, and then it gives you more details on the image type here. And this is happening at runtime basically. That is really advantageous when you want to test something, when you want to build dynamic clients, and so this is quite powerful, right? So now what we're going to do is go to the client, and I'm going to run this command. I'll show you the make file here. I'm going to do a make upload. So what it's going to do is basically going to uh, run the client binary and call the upload method, and then with the image path, and I've just hard coded a path here, which is going to be uh, that's me. Shout out to my wife for making this. So that's me, and I'm gonna send this image to the server and see how it's gonna destroy my pretty face. So let's run the, and then watch out for the edited directory. So in images, you see the edited directory. Okay, so now that the server is running and you have my image, and I'm gonna do a make upload. And as I told you, it's gonna run this command, and on the left side you watch out for the edited directory. So there's currently nothing in there, and then so I'm going to do make upload. So it connected to the server, it loaded the image, it saved the image, and then on the server side, if you look at the logs, it's applied the filter vintage filter, and it saved a file called vintage-diabe.png. And diabe is my Twitter. So if someone wants to follow me or reach out to me on Twitter or X, it's going to be diabe, diabhey. And in the images, you see that's the vintage me. You see the normal me, and then you see the vintage me. Let's keep running this command 2 3 times, right? And then I have multiple filters being applied. So you saw the file from the server, unstructured, serialized, sent over binary data frames, deserialized, loaded, a filter has been applied, and then saved, and then the information is the client receives the information. This is happening. And then we also mentioned about the synchronization with the object storage, right? So if you look into the logs of um, the synchronizer R clone, so these are the logs of R clone. So basically, a new file was detected and then uploaded to the Amsterdam Spaces instance, and then it's also copied to the New York and Sydney instance. Um, and let's just see this, and it's synchronizing, right? Let's try one more. I'm running the command make upload. So it's applied this filter now. Ooh, oops, this one. New file detected, synchronized, uploaded. All right. Now let's go to DigitalOcean's cloud control panel, and it's one of the most intuitive, simple cloud control panel you ever come across. Um, Pretty straightforward. You have the spaces bucket object storage here. And I've created three instances: one in Amsterdam, as you see, one in New York, and the one in Sydney. Let's refresh it. You should be seeing those files here, updated just now, 2 minutes ago, and see all the files. And the same files are also been synchronized to the New York data center instance and also to Sydney. Pretty cool, huh? So now let's go. And I mentioned something about the quick share, right? So now let's go to the vintage Diabe, right? And then create a quick share. It generates a file URL, so which you can copy, and you can set the share durations. Only want it for a particular time. Uh, you copied it, and for the time being, let's go back to our terminal. And the reason why I use a white theme, some might ask, is for accessibility, so that people are able to see things clearly. I personally prefer sometimes a dark theme or a light theme, doesn't matter. What really matters is, does your code work and you're able to be productive, and that's what I care about. Um, anyway, so let's curl up to and then say download.png and then pass this, right? And now here you can see the downloaded file, which we just downloaded from our Amsterdam data center spaces instance. So if you go back to the architecture, this is what we've covered so far. And that's it. That's the end of the demo, and I hope you're able to grasp something out of it, and feel free to try it out. The links to the repository and all the materials that I uh, use to reference, I'll share everything with you all, so you'll be able to yeah, might speed up your learning process. Thank you for attending the talk, and thank you for attending Deploy 2024.